Well, good morning, everyone. This is Mrs. Hanson, and we are continuing in our alcohols chapter, looking ahead now into section 4, preparation of alcohols via reduction. Both of these topics will come up in our chapter, both oxidation and reduction. And I wanted to just take an opportunity to reinforce in organic chemistry how we define the terms oxidation and reduction. So I'm going to begin with a review of the oxidation states and the relationship to formal charges, because they are indeed not the same. And I don't want us to be confused about how we're arriving at oxidation numbers versus assigning formal charge when deciding the best Lewis dot structure. So again, oxidation is really just a method of electron bookkeeping. This is a system derived by chemists to keep track of electron flow in the process of oxidation, which is the loss of electrons. The loss of electrons is oxidation. And then the gaining of electrons is reduction. So again, a classic definition: loss of electrons, oxidation; gaining electrons, reduction. So this is the method that chemists will use to just simply keep track of where the electrons are lost and where they end up going. So let's just review how we assign oxidation numbers, and then I'll contrast that with formal charge. We're going to treat all bonds of that atom as if they were purely ionic and break heterolytically, giving each pair, and this is a critical part, to the more electronegative element. So let's decide what to do with this example. Here we have carbon attached to a hydroxide, attached to 3 hydrogens. This is just methanol, an alcohol with 1 carbon leading to the hydroxyl group. Now, when we break a bond, this is different than formal charge. We're going to assign both electrons to the more electronegative element. In this shared pair of electrons, oxygen is more electronegative. It receives both pairs. Between the CH bond, which is a very close call, but carbon is more electronegative than hydrogen, so we're going to cleave the bonds heterolytically, meaning that all of the electrons in the CH bond are assigned to the carbon. So that gives us 1, 2, 3, 4, 5, 6 assigned electrons around the carbon. We know that carbon lives in group 4A, so it has 4 valence electrons, 4 assigned electrons. You can think of this as its group number. The group number for carbon on the periodic table is 4A, therefore it has 4 valence electrons. We just assigned 6 electrons around it, and therefore its net oxidation state is a +2. So the difference here is the way that we assign electrons to determine oxidation state. The number of valence electrons comes from its group number on the periodic table. The number of assigned electrons comes from a heterolytic bond cleavage, assigning all of the electrons in the shared pair to the more electronegative element. And in doing so, we find that carbon in this state is a +2 oxidation. Now let's compare that to how we would assign formal charge. Formal charge, we ended up breaking those bonds very differently. With formal charge, we broke those bonds homolytically. In other words, one electron in a shared pair went to each of those atoms. The way that I always like to show this, when we draw a molecule, and I had suggested this when we did, very first time that we met each other, we were practicing formal charge. I said, draw a circle around each atom, and in that circle you are bisecting the shared pair, and that means half of the electrons in a shared pair go in each direction. And so here you could see carbon would have 4 electrons assigned to it. For formal charge, carbon lives in group 4A. So here would be its valence electrons. it has 4 assigned electrons, and therefore its formal charge is 0. It has an oxidation state of +2. Whoops, its oxidation state is +2, but its formal charge is 0. So we just want to be sure we're making a distinction between the two ways that we electronically bookkeep. We're focusing in this chapter on oxidation state. So carbon, even though it has a formal charge of 0 in every one of these particular molecules, methane, methanol, formaldehyde, formic acid, carbon dioxide, the formal charge is all 0 because it has 4 bonds. And because it has 4 bonds, the formal charge is 0. Those are very valid Lewis dot structures. But again, this chapter, this section is oxidation and reduction of alcohols. So we're reviewing what those two terms mean. To understand if we're oxidizing or reducing the alcohol, we have to have an understanding of those terms. So remember in this case, we'll just kind of blow up this molecule a little bit. Here's the methane molecule. Now, in an oxidation state, the pattern says assign both electrons to the more electronegative element. And so therefore, when I cleave this bond, carbon is going to receive both of the assigned electrons around, around that. So hydrogen receives none, carbon receives all. So notice if we count now how many electrons this carbon is assigned. It lives in group 4, so it's assigned number there. 4 is the group number. But we have 8 electrons assigned to it, giving us a net of -4 for its oxidation number. Here we see in methanol, the oxidation state would change because both electrons now are going to be assigned to oxygen, the more electronegative element, and therefore that gives only 6 electrons around the carbon, giving it a net -2. Here carbon would lose both of these. The double bond brings all 4 electrons in this shared pair of a double bond. Those 4 electrons are all given to the oxygen. Both of those shared pairs in the single bonds, giving us 4 minus 4 as 0. And so forth. We can see now that the carbon loses both of these because it is now being drawn to the oxygen. And at this point, carbon is just assigned 2 electrons, still lives in group 4 with only 2 assigned electrons, giving it a +2 overall. And in carbon dioxide, it would have no assigned electrons. All of those electrons in the bonds would be assigned to oxygen, giving it a net +4 oxidation number. So when we track carbons are looking at assigned electrons. We can see a wide variety of oxidation states, and yet every one of these examples has a formal charge of 0. Just want to emphasize they are not the same vocabulary. If we have carbons bonded to another carbon in a longer chain, what do we do when we cleave heterolytically? So for example, here we have a carbon assigned to more carbon coming up to the oxidation in a carbonyl. So the answer to that is we can only split and arrive at giving all electrons to the more electronegative element. But if it's a tie, you're bonded to the same element, one is not more electronegative than the other, they're exactly the same element, that's when you cut the bond in half and you're going to assign 1 electron in each direction. So as we look at how we attack this problem, the carbon at the carbonyl has 2 assigned electrons, and that's it. And that's from cutting the bond in half and assigning the electrons 1 in each direction. And so if carbon lives in group 4A, and it only has 2 assigned electrons, this ends up to have a +2 oxidation state overall. So a reminder, if it's tied, if it's bonded to the same atom, then you just give 1 electron in each direction. So a good review to carry forward, just because the purpose of this entire section, if you recall, is the reduction of an alcohol. What does that mean, to be reduced? To be reduced says we are going from a higher oxidation state to a lower oxidation state. So for example, if I had a carbon at a +4 and it ends with a carbon at a +2, it has been reduced. It could go down to a carbon 0. It has been reduced. So going down on the number line in terms of oxidation state is a reduction process. So a reaction that involves an increase in oxidation state is called oxidation. And of course, if we have a reduction, we know that the number is decreasing. So oxidation becoming more positive, reduction becoming more negative. So if I lose electrons, oxidation becomes more positive, reduction will become more negative. And that must mean that we're gaining electrons assigned to us to have a reduction because electrons are negative. Let's put it into practice. Let's determine whether the compound has been oxidized, reduced, or neither. And remember our strategy. The strategy here is to assign the oxidation state for each center carbon and then determine if a change has taken place. And the focus is always on the carbon where the change has occurred. So here we have a carbonyl carbon, C double bond O, and now this carbon, the same bonds, same number of bonds coming out, but they're leading to an OR, so that's an ether group. So let's begin and just assign oxidation states to the carbons, remembering to break the bond heterolytically. So as we draw this one a little bit bigger, knowing that the carbon would not be assigned any electrons that lead to oxygen. Oxygen is the more electronegative element. Remember that these are two carbons, and this is the carbon that we're studying. Because it's leading out to the same element, we see that we break the bond right in half and we assign the electrons to one to each carbon. So the number of assigned electrons here is 2 for that carbon. Carbon lives in group 4A. It has 4 valence electrons. We just assigned 2 electrons for the oxidation state, leaving the net to be a +2 overall. Let's do the same over here. We have a 3 carbon chain. This time the oxygen in this particular carbon is going to be assigned in both directions, both shared pair. And notice here we're still leading out to a carbon-carbon. That backbone hasn't changed, so we cleave heterolytically. That gives us just 2 assigned carbons, so we have not changed the oxidation state. So again, this carbon ended up to be a +2 because both of the electrons in that shared pair went to the oxygen, and we simply cut the bond in half if we lead out to another carbon. Therefore, nothing was oxidized, nothing was reduced. It's neither. We started with a +2, we ended with a +2. No change in oxidation state occurred, so this is neither oxidation nor reduction. Here's a couple more just from your homework to give you a try. Why don't you pause the video and work these out and come back when you're ready to check your answers. Pause and think, then come back. Well, welcome back. Let's go through this example quickly and see if we have the same answer. Here, this is an aldehyde, the functional group of an aldehyde, which is a carbonyl carbon at the terminal end of a chain. So we have a carbon leading out to a hydrogen. We know to assign all electrons to the more electronegative element, which is oxygen. Here, the more electronegative element is carbon, and here we would have to cut it in half, assigning 1 electron in each direction. That leaves us 1, 2, 3 assigned electrons in that carbon. Carbon lives in group 4, so it has 4 valence electrons. We just assigned 3 electrons to it. leaving us an oxidation state of +1 overall. Let's try the same here. Here we have a functional group now of a carboxylic acid. Cool. That carboxylic acid then will assign all electrons leading to the oxygen to the more electronegative oxygen. So this carbon in the center has no assigned electrons that go up to the oxygen carbonyl or down to the OH, and we're simply cleaving this because carbon to carbon, we assign 1 electron in each direction. So carbon still lives in group 4A. Here we have 1 assigned electron, giving us a net +3 overall. And now we can see that if we started at a +1 and ended with a +3, becoming more positive is oxidation. Let's try the next one together. Assigning both electrons to the chlorine, assigning all 4 electrons to the oxygen. The carbon in this center here is assigned 1/2 of the carbon of the electrons in that shared pair, giving us again just 1 assigned carbon. So carbon lives in group 4A. There is just 1 hydrogen assigned to it, or 1 electron assigned to it, so we have a +3 oxidation state. And this looks very similar. I'm going to give both electrons to the oxygen, all 4 electrons to the carbonyl, and cut this one in half, giving us again just 1 assigned electron. Carbon lives in group 4. We only gave it 1 of those electrons, so this was a +3. So there was no change in oxidation. And therefore your answer here would be neither. It's neither oxidation nor reduction. So it's a way of keeping track of electron assignment. To understand to be oxidized or reduced, we have to understand how to assign oxidation numbers. Now the focus of this section is reduction. So these are the reagents now that are going to give us a reduction reaction. So just to kind of emphasize, here we have a carbon that would receive none of the electrons in the carbonyl and receive 1/2 of the electrons in a carbon-to-carbon bond. So we can see that this is starting at a +2 oxidation state. Carbon lives in group 4. We just assigned 2 electrons to it, giving us a net +2 charge. Here we have the oxidation state changing. Oxygen would have both of those, and now all of a sudden in this shared pair, notice that this carbon, as I was just drawing here, this carbon, I only see 3 bonds. So to perhaps make this more clear, we should just kind of emphasize, let's just redraw this, that's saying carbon now went from an sp2 carbon to an sp3 carbon. Don't forget that there is a 4th bond, and that bond is now going to hydrogen. So if it wasn't evident, we have to kind of make sure that we count all 4 bonds. And so this particular set of electrons wasn't essentially clear in this picture, so that's why I stopped to just redraw. The 2 carbons that are the same give just 1 electron in that shared pair. Both of these go to the oxygen, and both of the electrons in a CH bond are assigned, they're assigned to the carbon itself. So carbon lives in group 4. There's 1, oops, no. There we go. And we assign all of those electrons, having a little trouble there, sorry, giving us an oxidation state of 0. So this is reduction simply because we started with a +2 and now we're at an oxidation state of a 0. It's going down on the number line, becoming more negative is reduction. And we'll see that there are 3 reducing agents that we'd like to focus our attention on. 3 reagents that can accomplish reduction. Some of these are very familiar to us from previous chapters. For instance, the first one. Recall from chapter 8, using molecular hydrogen in the presence of a metal catalyst reduces an alkene to an alkane. Indiscriminate reduction. All pi bonds are reduced with a hydrogen and a metal catalyst. So here we have an example from a previous chapter where an ene, which is sp2, turns into an ane, which is sp3, by adding hydrogen across the double bond. We're going to see a very similar reaction occur for ketones and aldehydes because they also have a pi bond. The conditions here, however, are very rigorous. Very high temperatures and very high pressure must be used to force this reaction to occur. So although we can force the reaction, it's very rarely used in an actual laboratory because of these forceful conditions. But just to remind ourselves, hydrogen is an indiscriminate reduction agent, and any pi bond becomes reduced in its presence. So reduction. Here we started with a ketone and turned it into an alcohol. With very high pressure, very high temperatures, we can use molecular hydrogen in the presence of a metal catalyst. A second reagent, often used in the lab, is sodium borohydride. NaBH4 is how you'll see that on the arrow. Very common reducing agent. It readily reduces the ketone or an aldehyde into the alcohol, and it does so with a reagent NaBH4 where the boron tetrahydride. And let's kind of examine that. Remember boron, who lives, I said that from bromine. Boron, who lives in group 3A, its natural oxidation state has just 3 valence electrons from coming from group 3A. It would like to have just 3 to have a formal charge of 0. If we put 4 hydrogens around it, therefore, it must have an overall -1 formal charge. And of course, the Na there is a spectator, just making it electrically balanced, Na+, with the boron tetrahydride negative anion. Boron lives in group 3A, but we just placed 4 assigned electrons around it, giving it a formal charge of -1. So when you see the formal charge, boron -1, is just reminding us that typically it would only have 3 electrons to have a formal charge of 0. And so that negative charge on boron sets up a reducing agent because it's source of a hydride. Remember, boron would naturally like to have just 3 electrons around itself, right? 1, 2, 3. And so this hydride, this set of electrons here, ends up to be a very powerful reducing agent. If I can get rid of one of these hydrogens, take both of the electrons with it, it's essentially giving us a source of a hydride, H negative. And so I think about that in terms of its mechanism. It functions as a source of a hydride. And notice here we've carefully selected a protonated solvent, ETOH, ethanol, MEOH. Ethanol and methanol are protonated alcohols, or water, HOH. All give us a source of a proton for the solvent. So the function very carefully says we're going to need a source of a proton, and let's take a peek why. Here's our carbonyl carbon. This is the site of reduction. We start with a ketone. Remember that this boron tetrahydride is taking both sets of electrons from that sigma bond, from the boron, who has a negative formal charge. This is going to reach out to this electrophilic carbon. Remember, the electron withdrawing group from the oxygen is pulling the electron density away from the carbon, essentially making this a little bit positive. So the target is to take the hydride and attach it onto the carbonyl carbon, thus breaking the pi bond and collapsing it up to 2 extra electrons on the oxygen. So in the first step, sodium borohydride delivers a hydride, that extra hydrogen, to go now from an sp2 carbon to an sp3 carbon. We've added on a hydrogen, which then creates a more stable configuration for boron back to a formal charge of 0 in also an sp2 configuration. Now notice here we have an alkoxide. So this right here is a negative ion on the oxygen, again just based on formal charge as well, but it has an extra set of electrons. Remember, our goal is to turn it into an alcohol, so we need to protonate that negative oxygen. And that's what the function of the solvent does. The solvent must contain the proton so that when the oxygen reaches out for the proton on the solvent, we notice that that proton then transfers and this bond collapses onto the oxygen. And then, of course, hydroxide would be resulting from that proton transfer. So in step 1, we use the sodium borohydride, the reagent, to create the alkoxide anion. And then in the next arrow, we protonate the alcohol with the solvent. So this is the mechanism here. Notice here this nucleophilic attack. This nucleophilic attack has some very important geometry to consider as well. We started with an sp2 configuration on this carbonyl, and we ended with an sp3 on the alcohol. When we go from an sp2 to an sp3, recall that we can have a front door or a back door attack from that tetraborohydride. So if that nucleophile attacks from this side or this side, because the carbon, this ketone here, is an sp2 configuration, this carbon is trigonal planar, that means we're going to have enantiomers form through this process. So we could have the alcohol end as a dash or as a wedge in the enantiomer. So starting with sp2 and ending with an sp3, notice that you'll have both dashes and wedges form with this particular mechanism. So as we create those products, you have to consider the chirality center. There is a third reducing agent that I'd like to talk about, and it's very similar to boron tetrahydride. And that third is called lithium aluminum hydride. And you'll see that on the arrow is Li, lithium, Al, aluminum, hydride. Now notice this is very similar to what we just said. Sodium borohydride. Sodium was the spectator to keep it electrically balanced. And the negative anion of BH4. We have the same condition here. Aluminum lives right under boron on the periodic table. It has just 3 valence electrons. When we place a 4th bond around the aluminum, just as the same story with boron, because they're in the same family, we're getting a source of a hydride ion. And this here, the hydride, is that powerful base that can be used in this first step of the mechanism, putting on the proton into the carbonyl carbon. So notice there's a very similar structure. And again, lithium is just the front name to create an electrically balanced compound. So they look very similar in terms of delivering hydrogen to the carbonyl carbon. There is one very critical difference, however. Lithium aluminum hydride is a much stronger reducing agent, and I'm emphasizing, you can clearly see it reacts violently with a protic solvent. So here's the key. We must progress stepwise, making this very sure that all of the reducing agent has been completely removed from the reaction flask, either making sure that we put in a quantity that will be completely consumed through the chemical reaction, or removing it from the reaction flask before we add the proton into that solvent. So we have to do it stepwise. You're going to see very clearly step 1, add lithium aluminum hydride. And that step 1, just as you remember, is the proton transfer, where we turn the sp2 into the sp3 carbon. So again, very similar. Here's the aluminum tetrahydride. So here is the AlH4 negative. This proton is going to be transferred, creating an sp2 into an sp3. That's the same step, but now remember, this is absent of the solvent. Very critical is that the first step must be absent of the solvent, otherwise a violent reaction will occur. Once all of the lithium aluminum hydride is consumed or removed from the reaction vessel, we have a second step. And now that's to add the solvent to protonate the alkoxide anion and produce the alcohol. So let me just remind you, in our first one where we looked at boron tetrahydride, you see the reducing agent and the solvent sitting on the same arrow. You can add them together and there's no repercussion for that. However, if we use lithium aluminum hydride, which is a more powerful reducing agent, we must carefully do it in a stepwise fashion. Same stereochemistry to care about, that when we start with an sp2 carbonyl carbon as in a ketone, and we end up with an alcohol, which is an sp3 carbon, you'll have both configurations for a chiral center. The chiral center can spin in both directions, clockwise or counterclockwise, giving us priorities of R and S configurations. So we've had 3 reducing agents. Let's just review those quickly. The 3 reducing agents, we said the first was simply taking molecular hydrogen, sitting it on an arrow with a metal catalyst. This is an extreme condition. Extreme conditions means very high temp, very high pressure, and therefore hardly used. It can be accomplished, it's just not the preferred choice. Second, we use sodium borohydride, very commonly used in the laboratory, in the same reaction vessel with a protonated solvent. And a third, which is an even better reducing agent, but the conditions must be controlled to make sure that the reducing agent never comes into contact with the proton solvent, and otherwise we'll have a violent reaction. And so you'll clearly see that these are always on the clockwise, step 1, step 2. So here's everything that we've kind of said so far. We compare these reagents, starting with an alkene and a carbonyl carbon. So right here is the carbonyl carbon. Carbonyl, of course, we know is a C double bond O. And so this can be in a ketone. We can have that as an aldehyde. We know that that exists in amides or in ester. But C double bond O. And also notice that we have an ene, a double bond in this particular structure as well. If we were to add molecular hydrogen and sitting over a metal catalyst, doesn't matter which, platinum, palladium, nickel, just the presence of a metal catalyst, it's indiscriminate reduction. All pi bonds are reduced. So that means that molecular hydrogen is very efficient at going from ene to ane. And it's also very efficient at turning ketones into alcohols. All pi bonds are then saturated with hydrogen, very indiscriminate reduction. However, the last 2 tools were very particular to the carbonyl. So either using sodium borohydride in the presence of its protonated solvent, notice that we do not need stepwise fashion here, or in a stepwise fashion using lithium aluminum hydride, step 1, get rid of the reagent, then add the protonated solvent such as water. Then we can have the same goal. We can reduce the ketone into an alcohol, but it does not touch the alkene. So it's a selective reagent that will reduce the ketone to the alcohol, whereas hydrogen is not selective. All pi bonds are reduced. Let's put it into practice. Thinking about other types of carbonyl bonds. We talked about carboxylic acids or esters. Any type of situation where you have a carbon leading up to an oxygen in a double bond. Carboxylic acid, COOH, that's an acid. It contains a C double bond O. In the presence of excess lithium aluminum hydride, and in the presence of water, step 1, step 2, we turn the carboxylic acid into a primary alcohol. Here we have an ester. Again, here's our carbonyl carbon, just as above. Same reagent. And this time what we see is that the actual alcohol that's produced coming from here and actually cleaves this bond away. So let's take a look at this particular reaction mechanism. Just starting with the ester, we can focus our attention there. If we look at this carbonyl carbon, it's attached to a carbon chain, we'll just call that R, and it's leading out to another oxygen. If it's a carboxylic acid, we just put an H, or we could have another carbon. Here we're just having one more, so a methyl group. Same mechanism as above, we're just saying if I place in the aluminum tetrahydride, here's the aluminum, all 4 bonds giving aluminum a -1 formal charge because it only wants 3 electrons, so a -1. We see that both of these electrons reach out into this carbon, forcing this bond to collapse. So we're turning an sp2 into an sp3. So notice we have step 1 is the nucleophilic attack, turning the carbonyl carbon into a tetravalent sp3 carbon. So that very similar first step, we end up with this kind of configuration. All the dots around the oxygen. We still have OMe leading this direction. We now have a hydrogen delivered from our reducing agent. And over here is just that original R group left on the carbon as well. Now look what happens in a next phase of this mechanism. The alk oxide ion causes the carbonyl group to reform. So in essence, the leaving group is going to leave. Here is this negative charge. This extra set of electrons reestablishes the pi bond, forcing the OMe, the methoxide, to act as a leaving group and be expelled from this molecule. So we have the carbonyl reestablish. We get rid of it after we've added on the R and the H, and we've reestablished here an sp2 carbon. Now we do it again. We get rid, the first purpose here was just to get rid of this. OMe is gone. And we do now is just reestablish back to this time what we have as an aldehyde. Let's do it again. Take another aluminum tetrahydride, force it to connect to this particular carbon, deliver a next hydrogen, and you'll force this bond to break, reforming the alk oxide. We'll use finally the solvent in the last step of the mechanism to protonate and end up with the alcohol. So it takes 2 nucleophilic attacks to either deliver, this is true for both, for a carboxylic acid, or in ester, it takes 2 nucleophilic attacks to create the primary alcohol. And it does so by just expelling with this hydrogen. This group is coming out as well. So we're getting rid of this bond through a 2-step process and ending with the alcohol. So there's the mechanism of how this would work with a carboxylic acid followed by an ester. An ester, of course, we know is defined as this particular functional group is an ester. And as we think about the mechanism, this leaving group leaves, and we've essentially ended up with adding 2 more hydrogens on to create the alcohol. Let's draw the mechanism and predict the product. Well, again, I put these two on. These do not appear in your homework, but this is the goal. I see a ketone. This is a ketone, which is a carbonyl carbon in a carbon chain. I understand that in a stepwise fashion, lithium aluminum hydride is a reducing agent. And if I'm merely asked to predict products, it's quite easy. The ketone is going to turn into an alcohol. That's the function of the reducing agent. And then I will do so by producing enantiomers as well. But what we're asked to do is to actually show the mechanism. So we have a step 1, deliver the hydride, creating a chiral center, and then protonate that alkoxide with the solvent. So go ahead and give that a try, and let's see what we can come up with. First thing I'm going to do is draw in the aluminum tetrahydride, reminding myself that aluminum carries a negative formal charge because it has one too many bonds. This source of hydride originates the arrow and points up to the carbonyl carbon. That's an electrophilic carbon. The electron density is brought up to that oxygen. So then our first step, we're delivering the hydride. So when this happens, this carbonyl is now turned into an alkoxide negative ion because we've now delivered a hydrogen source to it. So this is the alkoxide intermediate. Now we use the proton from the solvent. So in the next step, you'd have a water molecule, and it then reaches out and deprotonates, collapsing this bond back onto the hydroxide anion. And we end up with a protonated alcohol, and of course the solvent is deprotonated due to the proton transfer and is floating out there as well, keeping in mind lithium would migrate towards it to keep it electrically balanced. So here's the mechanism for any of these attacks. Step 1, deliver the hydrogen to create from the sp2 into the sp3 intermediate. This is the alkoxide anion. In the next step, we see that the proton is transferred from the solvent. The alkoxide reaches out for the proton on the solvent. Remember, this is a water example, but you could use, for example, methanol, or you could use ethanol. Just a protonated solvent is all we need. And then you transfer the proton from the solvent and to create your alcohol. And remember, the stereochemistry is plus an enantiomer. The hydrogen could be the dash or it could be the wedge. You have a couple to try on your own. Try one from your homework with me. Pause the video and give it a chance. Come back when you have an answer ready to check. Okay, here we have our reducing agent. This time we're using sodium boron hydride along with a protonated solvent of just methanol. Here we have an ene. It's a pi bond, but this is a very selective reducing agent, and the selective reducing agent will not touch the pi bond in a double bond. We had said earlier, if I had seen hydrogen with some sort of metal catalyst on the arrow, then the ene would turn to ane. So that's not a good choice if you want to protect the double bond. So the first thing we'll recognize is the only site of reduction is going to occur at the carbonyl. Here we have a sodium tetraboride, so I show all 4 hydrogens, reminding myself that boron has a negative formal charge. The negative formal charge would like to be relieved. The purpose is just delivering a hydrogen to the carbonyl. So we reach out, and the site of attack is that carbonyl carbon, forcing the collapse onto this oxygen. So again, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Between carbon number 2 and 3, we have a double bond that is unchanged. And at position 5, we have the oxide anion that has formed, and we've added the hydrogen on. So we can just kind of show that the hydrogen has added on, although we don't need to draw a hydrogen. And in the next step, we see the process of adding the proton. So here we have methanol. We could see that this could be drawn as HOME, where the hydrogen is going to have then the job of being deprotonated from the solvent, and it collapses this bond back onto the oxygen. And so here, in the presence of that solvent, we end up with 1, 2, 3, 4, 5, 6, 7. Here's the double bond still untouched. We can make the alcohol come out as we could say the alcohol that comes out could be the dash or the wedge, because we know that we'd have the enantiomer form as well. So there's the mechanism of a reduction of a ketone into an alcohol. Step 1, we bring that proton onto the carbon, changing it from an sp2 to an sp3 carbon. We then, in step number 2, with the process of the solvent, we add the proton back onto that oxide ion, creating a protonated alcohol, OH. Every one of those will be the same for you in that particular homework set. If we turn our attention to making a diol, as the name suggests, are compounds with just 2 hydroxyl groups. So to name them a diol, we just have to let the reader know the position of both hydroxyl groups and identify with a number placed before the parent chain. So simple enough, the suffix diol, instead of just ol for a single OH group, we're going to end it with a diol with 2 sets of numbers to let you know the name. So here we have a 3-carbon chain, the root word there, propane. On carbon number 1 and on carbon number 3, we see a hydroxyl group. So this is 1, 3 propane diol. In this particular carbon chain, giving the lowest number, so here is carbon 1, 2, 3, 4, 5, 6 on 6 carbons. In the backbone chain gives the root word hexane. At carbon 1 and carbon 5, you hear the prefix ol. So 1,5-hexane diol. And we think about how to create these is really just the preparation, starting with just double batches of the same process. So really an indiscriminate reduction, no matter how many carbonyl carbons are in the particular starting reagent. Here I have 2 carbonyl carbons. We have 3 ways to get there. We can use the molecular hydrogen in a metal catalyst, an indiscriminate reduction, so all pi bonds are reduced. This is not a very favorable set of conditions. So this is extreme pressure, extreme temperature, and it's not really favored in a laboratory setting. Here we have a lithium aluminum tetrahydride or sodium boron tetrahydride. And it does allow me to emphasize, notice the critical importance of numbering the steps if you use lithium aluminum tetrahydride, but they are not numbered if we use the boron-based compound. Every carbonyl carbon will undergo the same mechanism as we studied in the last section, and we'd end up with a diol from each of those 2 carbons. A second way to prepare a diol is if the starting material contains a double bond, an alkene. And this goes back to reviewing some lessons from Chapter 8. If I go back to Chapter 8, Section 8.10, We learned how to change a diene, this ene, double bond, into a diol using a peroxy acid, a very strong reducing agent. A peroxy acid, just to kind of show you that structure, not only has the carbonyl carbon, but it has an oxygen group, that would be just 2, and then it has that second oxygen in that formula. So RCO3H followed by an acid source. Go back to section 8.10 and we can go through that. Well, I have it down here, I'll show you, but it makes an anti-dihydroxylation. If we use an osmium-based compound, OS is osmium, and I made a joke earlier in class about Donnie and Marie osmium, you create a syn dihydroxylation. That's section 8.11. These are the tools that we need to add to our toolbox, our reagents, to turn a double bond into a diol. We have to decide if we want that to add anti, which is 1-1 wedge, or a syn addition based on stereochemistry. You end with both dashes or both wedges. And I just went back into your chapter and took these screenshots to remind you how this worked. This is called a peroxy acid. So lots of oxygen there in that particular structure. And it goes through this intermediate known as an epoxide. And notice that these 2 carbons are bonded to 1 atom of oxygen. Because it's bonded there to 1 oxygen atom, we notice that we have an opportunity to attack from the top or the bottom on that intermediate, and thus you see the trans occur. So the enantiomer would simply have those positions changed on that particular structure. So a trans diol can be produced through a peroxy acid starting with the alkene. You had the peroxy acid, then you need to protonate the alcohols with the acid H3O+. And then I pulled this screenshot from your section 8.11 to remind you how the osmium worked. The osmium creates an intermediate where those carbons are attached to 2 different oxygens. So this is known as an ester configuration. See the difference? Epoxide has those 2 carbons attached to the same oxygen, leading to a trans addition. When they're attached to 2 different oxygens, you get the syn addition. Both will come out either from top or bottom. And so we don't have the opportunity for a configuration or an enantiomer. So that's pulled from a previous lesson, just the opportunity to go back and remind yourself from the notes you took there, kind of jogging your memory, that before in chapter 8 we had learned this tool, how to take an alkene and turn it into a diol. We're revisiting just because our topic in this chapter is alcohols. So let's remind ourselves that we've learned quite a bit of alcohol chemistry along our way. I'm going to pause the video here and come back in a minute, so you might want to do the same. Just pause, take a break, and come back.